Just trying to figure out which app has my camera on. Ah, there we go. All right. Hello, everyone. So I'm here today to talk to you about something I call infrastructure data, which I define as the data generated by your infrastructure. And so today I want to talk to you about the data that your infrastructure generates and how you can use that to have better insights and build better scalable distributed systems. So we're going to talk about increasing resilience, scalability, efficiency, reliability, and so on. And so the trick is you have to find the right data and present it in the right way so that you can build better systems. So what do I mean when I say second-order data? Well, for those of you who know your physics, you know that distance is the first order, and velocity is the second derivative, or the first derivative, and acceleration is the second derivative. And so I'm not exactly talking about that. I'm talking more about, look at this Google map, right? The first order data is the streets and the buildings. And the second order data is the places, the notary public, and these restaurants and things like that, right? So that is metadata. That is data that was put in there by someone else. Google derived it by driving around the streets, or people put it in, and so on. So that's metadata. But what's interesting is this. If you look here, you'll see that there's this whole orange section right there, right? And that orange section is a business district. How does Google know that? They've derived that from the metadata. So nobody told Google this is a business district. They derived that from their existing metadata. So it's not from the data, it's from the metadata. So that's what I'm talking about. And a lot of the stuff that I'm going to talk about, you're going to think, oh, but I'm already doing this. So yes, you probably are, and I want you to think about it in a different way. Also, some of my goals for today are to get you to stop keeping logs and to stop looking at CPU and memory and things like that, and to get you to start thinking more in groups, clusters, that sort of thing. And to think indirectly. Think about causes and second-order actions, that sort of thing, instead of just this creates this. It's this creates this and this and this. So first, let's talk about how do you set up your infrastructure to get this metadata in the first place. How do you create infrastructure that you will be able to derive from? It all starts with infrastructure as code. So you have to do as much of your infrastructure as possible in an automated way. Right? We want to automate everything that we can. We want to automate startup, deployment, configuration. Everything that can be automated should be automated. There should ideally be no manual process anywhere in your production system, because every manual process means human error, it means untracked changes, it means things that could be changed without anyone, well, that's untracked changes, but you know what I mean. And so, at my startup, we use CloudFormation for everything. Even the smallest things in the world, like adding a single group, we'll use CloudFormation to do it. No manual processes, just to make sure that everything is tracked. We know how everything is being taken care of because it's all automatic. There's some challenges with doing infrastructure as code. You can lose track of things. You can get configuration drift. Snowflakes, you get things that end up being different because they didn't get picked up in the changes. But these are all things that we can detect, and we can fix, and we can work around. So you can do this with pretty much any API-based infrastructure. So a cloud provider, Azure, Google, Amazon, your on-prem cloud, your on-prem containers, any container serverless system. So this isn't just in the cloud. It works well in the cloud because that is sort of by nature an API system. But you can set up your on-prem just as well with APIs. So first you have to choose your unit of compute. There's typically, you've got VMs, you've got containers, you've got serverless. And so for me, the way I decide is basically I ask these questions, right? Do I want control over the machines? Do I want control just over the applications? Or do I just want someone to run my code for me? And typically my answer is I just want someone to run my code for me. In my mind, containers are for code that you buy. So code that you write, anything that we write serverless. And then anything that you buy, you put in a container because you can't really buy serverless software yet. And when I say buy, that also includes things that you download for free that are open source. You're just buying them for $0. But basically, things that other people write, put in containers, and then things that you write, put in serverless. At least that's how I do it. That's the goal state for me. Because serverless computing is all about removing the overhead. And so this ends up being really relevant to your monitoring, because then you don't have to monitor it, because someone else is taking care of that problem. There's a few things with serverless that you need to monitor, which I'll talk about in a little bit. But overall, it saves you a lot of the work. And I'm not the hugest fan of containers. I don't use containers for a lot of things, mainly because they just sort of add overhead, and they break a lot of reliability abstractions. So what do I mean by that? So containers are great for deployment. Containers are a great way to say, do this thing on my laptop, make it look exactly the same in dev and test and production, and so they're great for that. But the problem is when you start putting multiple containers onto one machine, you rely on the bin packing of whatever orchestration you're using to do it the right way. And it's hard enough to rely on your cloud provider or whatever to distribute your application across the machines in an effective and smart way. Now you're adding another layer of complexity with your orchestration software, which now has to understand where the virtual servers are and what the application is doing and try to lay out everything the right way. And we're just not there yet. There's no great orchestration software that says this is the ideal place to put every container to balance out my CPU and to balance out my memory and all of that stuff. And so it's just another thing to worry about, which is why I try to avoid containers. If I do containers, I try to put one container per VM. So I use it more as a way of deployment than as a way of efficiency. But you can do it the way you want to do it. But as long as you have good monitoring, good observability, at least you can work around those. I just don't like to do it. So let's talk about observability. So what do I mean by observability versus monitoring, right? Monitoring is collecting metrics, bringing in data. Observability is more of an inherent piece of your overall architecture. It's designing in a way that makes things easy to figure out. So it's making sure that you have clear divisions of work, making sure that you have places to log everything, making sure that you understand what's being logged and where and how to get to it, making it easy for people to put log data and tracing data and so on. So observability is more about logs and metrics and traces than it is about monitoring software. Monitoring software is, of course, a big piece of it. Then there's also the differentiation between WhiteBox and BlackBox monitoring, right? So BlackBox is this idea of I'm looking at the system from the outside. I want to see sort of the emergent properties of the system, whereas WhiteBox is I'm looking at it from the inside. I'm looking at the code. I'm instrumenting the code. I'm emitting metrics from within the code to the outside. And so you really have to have both. You need to have that black box monitoring so that you can see what changes are happening that maybe you didn't catch with your white box monitoring. But you need the white box monitoring so that you can see what's going on, so you can get the deep insight necessary to figure out problems, to dive into those problems, things like that. Logging with Decorators is a really good way to get that white box monitoring. So if you're familiar with Decorators, it's basically a kind of a wrapper that you put around your function. So this is my Python decorator. You basically give it a function. You can give it optional tags, labels. And then what it does is it essentially grabs all the data that was put into that function, which is already in the event because I use serverless. And so it pulls all that data out, and it adds the extra labels, and it puts that all into the log stream so that I have all of that data with every function call. Now, this is a stripped-down version of that. The real version would have it be able to be turned on and off on demand, which I'll talk about in a little bit. And you'll notice the to-do there in the middle that says sanitize the data. So you don't want to be logging credit cards and passwords and things like that into your log files, because that's just a nightmare for privacy, especially here in Europe with GDPR. So you got to have a good sanitization function in there, which is just marked as a to-do because I live in the United States, so I don't have to worry about GDPR yet. But then it's also really important to do testing on your logging, right? So a lot of people forget about this. When they're if they're building tests at all, they're building tests around their software functionality, but they're not building tests around their logging functionality. So they don't know if their logging is actually logging the right things at the right time. So if you want to have good observability, it's really important to make sure that you actually build tests for your logs. So something that a lot of people forget about. And then if you are going to use containers, like I said before, I'm not a huge fan, mostly because without containers, you basically have your server, your virtual machine, your application. But with containers, you're shoving a whole extra thing in the middle there that needs to be monitored, that does its own things. And there's not great container monitoring solutions out there. Docker will give you the stats, and there's a couple other software that will give you some pretty graphs around CPU and memory usage of your containers, maybe something a little bit about their layout, but it's really hard to get good data about what your containers are doing. So it sort of complicates the issue. And that's why, like I said, I like serverless, because a lot of that is taken care of for you. There is some monitoring. You can get data about timeouts and how many simultaneous invocations you have. But for the most part, you can sort of forget about it. So you can just sort of push out that infrastructure. In my case, that's Amazon's problem. You can make it Google's problem, Microsoft's problem, but it's not my problem, and that's the important part. So once you've built this system, you need some actionable metrics. So these are some very old metrics from Reddit. And when you look at this graph, what do you see? You see that there was obviously some sort of problem. So the graph on this side is cluster status, and you can see that there's errors and that the request rate is bouncing around, and you can see the network has problems. But this doesn't really tell us much. It just tells us that there's a problem, but it doesn't tell us why. We can add more metrics into it, and it just still doesn't particularly help us because the sessions have gone up. And so all of this has done is told us that there's a problem. But it hasn't told us a solution or led us towards one. And so when I was at Reddit, we never got to the point where we could get solutions out of our monitoring. All we could get was notification of problems. Solutions came from digging in. So how do you get to solutions? Well, when I moved on to Netflix, we had started developing things that helped us get to solutions. So the first thing I want to talk to you about is double exponential smoothing versus static thresholds. So this is a good example right here, right? If you have a graph that looks sinusoidal like that, a big drop may not be a problem. In this particular case, these are not problems, right? This is just normal traffic patterns up and down. There's no way that you could put a static threshold on this graph that would make any sense, unless you had it constantly changing throughout the day up and down. So what we did was we did double exponential smoothing. This is basically, you can think of it as a Fourier transform on the data. And so it creates these bands of predicted traffic or predicted output of the graph. And so the bands are where we predict the line should be. And so the alerts only fire if they're outside the bands. And so on these three graphs, you can see the yellow bars are where the bands have been violated. And the first graph is with a 10% smoothing. The next is with a 20%, and the bottom one is the 0.5%. And so you can see it's very important to tune your smoothing correctly, because if you make the bands too wide, there's no alerts, even when there's problems. And if you make the bands too tiny, you'll get alerts when there are no problems. So you have to tune your smoothing, you have to tune your percentage. So we built an alert tuning function. Essentially, the top graph is the prediction, or the metric, and then the greens are the prediction. And so the bottom graph essentially redisplays that data as here's where the bands will be with that particular level of smoothing. And so you were able to dial in, and you could look at your historical data, and you could dial in the tightest band that still kept all of the violations outside of it, whereas all of the non-violations were inside. So that was an important piece of the puzzle, being able to tune the metrics and alerts around these changes, these bands, which led to what's now open source. So this is the Netflix monitoring system, Atlas. It's very similar to something like SignalFX or Datadog. They can do these things as well, where you can essentially do math on your time series data. And that's what's being shown here, right? So the blue is the actual metric, the red is the predicted metric, and the green is essentially just the difference between the two and whether the bands have been violated. And so when you do your alerts, you essentially say do an alert anytime green is 1. So at the end of the day, it is a static threshold, but it's on that second derivative of the data, right? So the first derivative is the predicted, and the second derivative is the band itself of whether it's been violated. So it is, at the end of the day, a static threshold on something that can have a static threshold because the value is only 0 or 1. And so this is how basically all of the alerting systems at Netflix worked, and if you use Datadog or those other things. So how do you choose which metrics to monitor, right? The first tip I give is choose business metrics, not machine metrics. So this is where I will tell you about why I don't monitor CPUs and memory and disk space. Because it goes along with this one, choosing groups and not individuals, the two together, right? So I don't really care if one particular machine in my cluster is using a lot of CPU or memory, because especially in the cloud, I'll just get rid of that. So I still want to track that metric, but I don't want to keep that metric around, because essentially once I've tracked it and realized that that machine is out of line, I'm going to get rid of that machine. And then I really don't care about those metrics anymore. If the problem continues to recur, I can go into the monitoring system and say, instead of deleting these metrics, keep them around, so I can try to diagnose this problem. But if it's just a random one-off, I'm going to assume that it was a machine problem or something that's transient that I don't care about. And so that's really my mindset in general, is transient things I don't particularly care about because I can just get rid of them. If they keep recurring, I might care about them. And then business metrics is a good thing to monitor instead of machine metrics, because really at the end of the day, you're trying to deliver a product for your customer. And the only thing your customer cares about is whether your product works. Right? So at Reddit, the business metric was, are we actually serving comments and listings and votes, etc.? At Netflix, it was, can people play their movies? That's all they really care about, can they play their movies? And so that was the main metric that we monitored, we alerted on, was how many people are playing movies at this very second, and is it within our prediction? And then we would look at clusters of machines to determine which clusters had issues, right? So we would look at their business metrics. Are they sending licenses? Are they giving out CDN URLs? Things like that. So more business-related, application-related metrics. And to make sure that we had all the metrics we need, self-service was key. And this is true pretty much anywhere, right? You want to give your developers the ability to inject whatever metrics they want into the system. Because that is what will give you those business metrics that you need to start making your derivations. And it's really important for the engineers who are writing the software to be able to put in the metrics that they think are the most relevant to their software. It's a lot harder if some operator is trying to determine what are the best metrics. It's much better when the engineer does it themselves. So the trick was a self-service system where they can graph their own dashboards. Anybody can put any metric in. Anybody can graph any metric. Anybody could graph multiple metrics together and correlations of those metrics. So we would have examples where I would graph my downstream services because I would want to get an alert when all of them were overloaded at the same time, because I knew that if those 3 got overloaded, I would have a problem in a couple minutes. And so it would give me an advanced warning of a problem, for example. And so it also allowed the ability to make it easy to track these business metrics, because then everybody can put it in by itself. And then another really important aspect of the monitoring system and an important tip is to alert on the increase of failure, not a lack of success. So that goes back to that other graph, right? Every night, traffic would turn down automatically because that was just the normal pattern. If we had alerts on traffic, it would fire every night. So you don't want to alert on a lack of success. I want to know that there's been an increase in the failure rate. Or if I'm diverting traffic from one cluster to another, especially in a very large distributed system, you want to alert on increases of failures. Because if you are changing things around, you might have a drop in success that's totally normal and expected. You also want to make sure that you've built tracing into your system. So this goes back to those decorators. Another good thing that you can use the decorator for is tracing the request. So you can pass through a request token identifier, start at the load balancer, all the way through your entire distributed system. So you can track them. There's a bunch of tools to help you do this. AWS has X-Ray. There's also Jaeger, which Uber uses. There's Zipkin. And then there's this example of the tool. Oh, that does not show up well on that screen. Example of a tool that Netflix built Essentially, if you could read this, you would see that it's tracing that one request from the top tier all the way to 2 requests to the second tier, and there would be a bunch of lines coming out to the next tier. But there's lots of different ways to do request tracing, and request tracing is a really great way to find out where all the services that were involved in a request, and then you can use that to correlate data back to your other metrics, your business metrics, which I'll show you in a minute. But first, I want to take a quick diversion down to talk about percentiles. So for how many of you does this mean something, P50, 90, 99? Okay, so a couple people. So that's good. Essentially what I'm talking about are percentiles, right? So imagine that we have this graph of response times to an HTTP request. And if you're just looking at the average, which is what most monitoring systems default to, is the average response time, it'll be that line on the bottom, the blue one, the 50th percentile. And everything looks great at 50th. Even at the 90th percentile, everything looks pretty good. It's when you start looking at the 99th percentile that things don't look so good anymore. And that may be okay. It depends on your business use case. If your business is okay with 1% of your customers getting a really terrible experience, then that's fine. But it's good to know that. It's good to have those percentiles, because then you can focus your efforts on what metric do we want to improve. Do we want to make everything better for the average user, or the 90% of the users, or so on. And even with large amounts of data, it's possible to determine percentiles. There's an algorithm called T-Digest. It's just a couple years old, and it's been used for by a couple of different large companies, and it's built into Elastic. And you can essentially determine percentiles without having to analyze every single piece of data. Because normally the way you would do 50th percentile, that's essentially a median. You'd have to take every single data point and figure out where the middle is, which you can't distribute over multiple machines. T-Digest essentially distributes that calculation across multiple machines. It essentially builds sort of the shape of your data and then estimates where each piece of data fits. And it's very accurate. It's less accurate in the middle, and more accurate towards the edges. So if you care more about 99th percentile, it'll actually be super accurate. But even the inaccuracies are only like less than a 1/10 of a percent. So it works out really well. You can make pretty good inferences from that data. And that's really important because if you're familiar with this concept of Anscombe's quartet, these 4 graphs are all based on the same data. Not the same data, but the data has all these same properties. So they all have the same average, they all have the same variance, and so on. But as you can see, they're very different graphs. And so when you're not looking at blocks of data, percentiles, you can get very different results based on the single calculation that you make. And so it's really important to get multiple calculations. And that's why that stacked graph of multiple percentiles is really helpful. So when you look at that stacked graph, you could see 50, 90, 99. You could see how things were shaping out. And then I want to take one more quick diversion down to talk about queuing as well, because queuing is really important. So if you look at this graph, you can see that the queue went up, and you can see that something happened, right? And we want to monitor queue depth. So monitoring queue depth gives us tons of insight and tons of things that we can derive off of. And queue depth itself is really derivative data. It's derived off of the inputs and outputs. But what's really important is from this graph alone, you cannot tell what is going wrong, right? Is it slow on processing in or slow on putting things out? So how many are familiar with the cumulative flow diagram? Excellent, only 1 or 2 of you. I love teaching this to people because it's like the greatest thing I've ever seen, and I want to tell everybody about it. So if you look at this, you immediately know where the problem is. You can see that the problem is that the processing slowed down because the input rate stays the same, it's the top line, but the output rate has a break. And so now you know exactly where your problem is. You can look you know where to focus. You know to focus on the processing, and you know that you need to increase your consumers. So this graph is great because it gives you that data that you need. And it's important to note that capacity utilization increases exponentially with queue increases. So every time you reduce the excess capacity by half, you get exponential increase. And so this is really relevant because if you see that exponential increase, you know that you have to double your consumers, for example. Or if you're very flat and then you cut half of your consumers out and your graph barely moves, then you know that you're very over-provisioned. So it's important to understand this basic queuing theory because then you can start playing with your consumers and producers and you can understand the results of that. And variability also increases with queue size length linearly. So that's good to know as well because you don't necessarily have to worry about massively increasing your consumers or producers if you see a linear increase. Actually, I'm just going to skip right over that because it's not that important. So putting queues everywhere is great for monitoring because then you get lots of great insight. And then the last thing I want to say is about logs on this part. So I'm not a big fan of keeping logs around. I don't find them super useful. We came to the same conclusion in Netflix. It was just a huge effort and infrastructure to maintain logs that nobody ever looked at. We actually ended up building a system that essentially lets you say, these are the logs I'm interested in, and only store those for a small amount of time in memory so they're quick for querying. And then you could output it to longer-term storage if you really wanted to. And so the way this would work is if there was a problem, we would then turn on logging for the things we thought would lead us to the answer of that particular problem. So we didn't have to have this huge infrastructure of logging. Now, of course, we couldn't look back at history, but typically, if a problem didn't reoccur, we didn't really care that much about it. I would only care if it reoccurred, and if it reoccurred, we could turn on logging. And so this would allow us to not have this huge infrastructure of logging, just giving us the data that we need. And then we also had problems where we would have outages, and it's easy to track. We would know that something is wrong. We would get an alert. We would be able to find the problem because we had telemetry, but we wouldn't necessarily know what changed in our system. So there's change control, which you could use. But the problems with change control are that it's manual, it takes a lot of effort, people just don't do it, they skip over it, and things like that. It was good because it would force you to think about what you were doing and get approvals, but that's not necessarily good either. So how do we solve that? We solve that with event logs. And so again, this was moving a manual process to an automated process. And that was our constant theme, right, is move from manual to automated processes. So the event logs, because we had an API-controlled infrastructure, we were able to output a stream of events without having to do any manual work. And so then this gave us another piece of data that we could correlate with other things later. So the solution was pretty simple. It was a very simple API. Anytime any change happened, it would output an event that would have this body of the request. And then we would have this log of every single change that had happened in the system. And again, manual things bad because they wouldn't get logged. Manual changes wouldn't necessarily get logged. So automated infrastructure, automated reporting gives us a very accurate change list. Then we didn't need change control anymore. We didn't have to worry about getting approvals and who was doing what, because we already knew, because the system was already outputting all of that information. So let's put this all together. Now that we've built our infrastructure for monitoring, what are we going to do with it, right? So a single metric in isolation isn't very useful, because then the alerts on those metrics aren't going to be useful either. And what do I mean by that? Here's a single metric. Something is broken. We're going to alert, this would be the graph of the load balancer. So we're going to alert the load balancer team that something's wrong. During that same outage, this graph happened, and this is the play requests. So we're going to notify the playback team that something is wrong. This is the customer service call volume. So we're going to notify customer service that they need to staff up because there's a lot of incoming calls. And each of these three groups aren't really going to know what the problem is that they're trying to solve. So we have 3 metrics on 3 services that go to 3 different groups. And so we need a correlated alert. We need an alert that went to one group that could go dive into this problem. So how do we do that? Well, we started with this eyesore of a chart. So this is essentially a graph of many, many metrics in a system where you could click on a single graph and say, give me all graphs that correlate to this one. And so we could find all the graphs that kind of correlated with that single event. During an outage, this was not the most useful tool in the world. However, after an outage, this tool was very useful in helping us figure out which metrics we were going to correlate together to build new alerts from. So we had that tool that would help us find all the correlations, so we could go back to an event that had happened, say this graph was the most direct leading indicator, let's look at all the different other ones that correlated with it, build a new alert, send that alert to the right team that would solve that, so that hopefully in the future that right team would immediately get an alert and know that something was happening. Then in the future, instead of sending an alert to a team, you would send an alert to a system that would automatically remediate in the ideal case. Obviously, you can't do that every time, but that would be sort of what we were working towards, was automatic remediation. And so almost everything was built on those time series data, on the metrics of time series and correlating time series data together, deriving data of taking multiple correlations. Sometimes we would also input change log systems. So you would take these 3 graphs and then look for a change in these particular clusters that happened at the same time, correlate those together, build an alert. We had another system. This was actually a really clever hack that worked really well. Every alert that you received, it had a simple button that said, was this useful, yes or no? And you would just click yes or no. And then you could go back and get a report of every alert that fired and what percentage of the time it was deemed useful. And so you could say this alert was deemed useful only 10% of the time. You may want to consider canceling it. Or you could say this alert was deemed useful 95% of the time. You may want to consider sending it to more people. And so that's that one little hack, that one little change we made to the email drastically improved our alert quality. Because what we had figured out was that there wasn't actually any correlation between number of alerts and broken things in our systems. Sometimes a lot of things would be broken and there'd be no alerts, and sometimes there'd be a ton of alerts and nothing was broken. So just adding that one little button made a huge difference. I want to talk real quickly about some other types of derived data that you can use in a system. So this is sort of the ideal microservices architecture. In the continuous deployment area, you could have something like OS query that will tell you what version of Apache you're running, for example. And that can be useful, but if you have, say, all of your machine data in a SQL interface, you can combine those together. Now you can really start getting some cool derivations, right? You can see that Apache is running on all these different systems, and you can figure out which particular machines are running them and what version they're on, and then you can say why are some of these different than others. You could go up higher and you could classify. You could look at the tags on those machines and see which different clusters they're in. Maybe one whole cluster is behind. You can also look at all the open ports, which we'll come back to in a second. But here's a nice visualization from Netflix. This is a thing called Flux. And this is a way to visualize the movement of traffic. And so this is based on the data, the logging data that this is based on is number of incoming requests on each individual cluster and number of outgoing requests. So there's nothing that's actually tracking the movement between them. It's deriving that movement from these pieces of data. And so this is an example of a shift in traffic away from one particular region. And so this visualization is real nice. You can see it change over. And all of this is just based on the individual logging of every single machine in each of those regions. And so that's all getting rolled up together and then deriving this traffic flow data from it. There's no monitor of actual flows. And so this gives us a nice isolation. We don't have to have an agent that's listening and watching for data leave one and enter another region. It's being derived from the data that's coming out of there. Another one I want to talk about is rendezvous hashing. So how many of you are familiar with this concept, rendezvous hashing? I love teaching people this one too. So don't worry about the math. The math is super complicated. But essentially, at the end of the day, what this is a way of choosing which cache you're going to go to, or not necessarily cache, but anytime you have a distributed system where you need to figure out where to go get data, you essentially use that formula to calculate which server you're going to go to by running that formula over all possible servers, and then going to the one with the highest number. And so the reason this is great is because if you have a loss of a server, the way the algorithm works is that it will spread the data around very evenly across your remaining cluster, so you won't get hotspots. But why is this interesting? Because you can visualize the outputs of the rendezvous hashing. So for every single hash you calculate, you can log that. And then you can put it onto a map. And if you're familiar with the XKCD fractal layout of the internet, essentially if you lay it out in that same fractal pattern, what you end up is getting the same machines next to each other. And so if you visualize it and you see this kind of pattern, then you can see that you have a problem. You can see particular machines are not being selected, so you probably know that you have an outage. And again, this is great because it's completely isolated. You have individual machines reporting their hash functions, and you can derive what is going wrong without having to monitor each individual machine because it's being derived. And so this is going to be probably more accurate because maybe your monitoring on that one machine will be broken. But from here, you're getting tons of data points, all isolated. If some of them don't come in, it doesn't matter. And you get this broad scope, and so you can see it. More places where you can derive. If you have all of your instances, you can roll it up by tags, and so you can see which clusters are costing you more. Again, automated infrastructure means you're tagging all your clusters, and so that's an important piece at the beginning where you need to be tagging those clusters. And then you can get that data. You can do canary analysis. So this is a product. This is Spinnaker. This is the commercial version from Armory. And they do automated canary analysis, so you can derive from your data. So this is business metrics coming out of your regular cluster and your canary cluster. And so you can automatically determine that your canary is being successful or failing based on that data. And then going back to our open port map from before, we can now start deriving some really interesting data from that. So we can say, where's port 443 open? We get a list of instances. We can dive down further and say, where is port 443 open on security groups that have that open? So where can it be accessed from? And then we can drill even further and say, which ones are running Apache? So now, combining running Apache, open on 443, in a security group that allows that access, we can see where we need to focus our Apache upgrades and our remediation on the ones that are actually internet accessible, so we can start there, be more secure. So those are just some quick examples of ways you can use derived data from multiple different sources, putting it all together to get isolated data together to get good insights. So finding the right second-order data is essentially what will help you build better systems. I think now we're going to switch over to the questions. Thank you. What is your opinion on managed Kubernetes clusters where you use containers but you don't need to manage orchestration? So managed Kubernetes clusters are great. They definitely help get rid of the overhead. You're almost to the point of serverless, because that's essentially what serverless is, right? Is they're managing these containers for you. It's almost serverless, so it's pretty good, I guess, is my opinion. It's still slightly worse, only because the serverless stuff is designed for very quick startup and very quick teardown, so it's easier to be managed. But overall, a managed Kubernetes service could work. It means you're offloading it to someone else if you trust that someone else. It really comes down to your trust of that other person who's running the system. If you don't keep logs, what do you base your decision? So the logs would be machine logs that I don't keep, right? So all of the errors and things like that. Logs of business metrics are kept. And so making business decisions around business metrics is still possible because we still have all of the time series data about business metrics. If there's particular business metrics that need to be logged in the application, you can log those separately. So like I said at the beginning or in the middle, we'll log certain things we'll turn on logging for and keep them on for the amount of time necessary. In the case of business metrics, sometimes those will be kept on for a long time, especially if you want to track particular users or things like that. But you got to be careful with those, with the privacy and all that. But mostly what I'm talking about is like machine logs, like syslog types data is the stuff we don't really keep. Without logs, you lose the ability to pre-detect errors, resulting in bigger issues. So, like I said earlier, if an error occurs and then goes away, I don't really care so much about it. If an error reoccurs, I will start logging it, and I will keep those logs until I solve the problem. So that's the main workaround around that. Now, the big, huge caveat here is if you're doing security auditing, you do need to keep your logs because you do need to be able to go back in time and look. So if you have a security need or you have an auditing need, say because you're a public company or you're under various privacy laws, then you may need to keep those logs around for those specific use cases. But as far as operationally speaking, I don't find them super useful, even for pre-detection of problems, because the logs will be generated on the machines. I just don't ship them anywhere to save them. So I just let them sort of die with the machine. And so you can still analyze the logs on the machines, and you can still create alerts out of those logs in the individual machines, which actually offloads a lot of the work as well. So that is one way to sort of get around that problem. We experience a problem that autoscaling is not fast enough. This is a good question. So the key to autoscaling is your startup time. The smaller your startup time, the better your autoscaling will work for you. Because essentially, whatever your startup time is, that's how early in advance you need to predict a scale up. If your startup time is 5 minutes, you need to be able to predict your traffic 5 minutes in advance. If your scale up is 5 milliseconds, you only need to predict your traffic 5 milliseconds in advance. So the key to autoscaling is minimizing your startup time to be as small as possible. That is pretty much the only solution. You can attempt to predict traffic. There's tools to do that. Amazon has tools to do it. I'm pretty sure Azure does too, where you can attempt to predict traffic and get ahead. At Netflix, we built an entire system of predicting traffic. So one example was on Saturday mornings, kids would wake up and watch cartoons, and there would be this huge spike on Saturday morning of viewing. And so we could detect that and scale up ahead of that. But generally, the quicker your startup time is, the faster your autoscaling, and the more successful you will be at autoscaling. Why not concentrate on more passive monitoring? I'm not quite sure what you mean by passive monitoring. I don't know if the person who asked it wants to yell out, but yeah. Mm-hmm. Okay, so I mean, I don't really see a difference between that and the time series metrics and looking at the time series metrics. So, but like I said, you could look at the logs on the machines, monitor and create insights out of that without shipping them to one central place. It sort of depends on your system. If there's a kind of logging that will get you good insights passively, my suggestion is to put them in the software and send them to a separate service, and make a service that's specifically around logging for that one type of metric, instead of trying to extract them out of the syslogs and put them in the right place. Because the syslogs are full of a lot of useless stuff, right? They're full of everything that every application you're running is outputting the syslog. And so if you want to log a specific thing, you could either grab it out of that individual machine and ship it off. And that's kind of what that log thing that I showed you does, right? Where it scours the logs for the specific things you're looking for and pushes them to somewhere else for passive monitoring.
Okay, we do not have time for more questions, so thank you so much. This is a little gift from the organizer team, and it's a picture of you.
Oh, wow. Thank you very much.
Thank you so much for coming and talking here at Craft.